All right, let's jump right into this explainer. Today we're decoding what honestly reads like a paradigm-shifting technical manifesto from the folks over at emerging.systems. It's called the Consensus Hypervisor, the Phoenix release. Now, if you follow advanced computing architectures, you know the drill, right? We usually get these tiny iterative improvements, a slightly faster cache here, maybe a tweaked branch predictor there. But this source material? Oh man, it proposes tearing the whole house down and literally rebuilding it from the silicon up.
And you can see just how audacious this claim is right here. Nick, the author of this manifesto, is stating we need a foundational break from the von Neumann architecture. Think about that for a second. The von Neumann architecture has been the absolute bedrock of computing since, 1945? It's that fundamental idea that your computer has a processor doing the math and memory holding the data, and they just talk back and forth. But Nick is proposing we abandon that separation entirely. We are fundamentally redefining how a computer operates at the bare metal.
So what happens when a computer is treated as a topological lens instead of just a calculator? This one question anchors the entire text. It challenges us to look way past traditional processing and embrace this wild concept of absolute silicon sovereignty. Instead of a machine linearly crunching ones and zeros like the phone in your pocket, imagine a system that warps and bends data through a multidimensional mathematical mesh, a topological lens. It's a mind-bending, almost sci-fi concept that totally forces us to rethink what software and hardware actually are.
To wrap our heads around this, we're going to unpack this complex C++ architecture step by step. We'll hit the sovereign thesis, dive into sub-Shannon storage efficiency, check out the Neumann bypass, explore the Obsidian workspace, and finally, look at the Baumgartner puzzle.
Okay, Section 1, the sovereign thesis, redefining the machine. Let's see how they build the mathematical foundation for this whole thing.
In a traditional von Neumann setup, you've got the calculator, right? The CPU. It fetches data, runs the numbers, and puts it back in storage. It's totally traceable, but the consensus architecture acts as that topological lens we mentioned. By mathematically unifying the storage layer and the execution engine, it achieves what the author calls complete forensic invisibility. The data and the logic used to process it become totally indistinguishable within the physical hardware. It's like you literally can't separate the map from the territory anymore.
Now, the framework is rigidly broken down into these topological tiers. You've got an open evaluation build capping at 1 terabyte, a hardened enterprise release for 10 terabytes, and then it culminates in the VFX sovereign build, which boasts, get this, unlimited capacity. Yeah, literally unlimited. Go ahead and apologize to your current hard drive, because how in the world do you get unlimited capacity out of finite physical hardware? Well, that brings us to their next massive breakthrough.
Section 2, Sub-Shannon storage efficiency, breaking the limits.
For decades, computer science has treated Claude Shannon's limit as gospel. It's the physical law saying you can only compress data so much before you start losing information. Well, consensus claims they broke it. And the crucial point here is that this is not your standard zipping algorithm. It uses an engine for what it calls recursive phase folding. We are talking about evaporating data into pure mathematical residue. Imagine a highly structured operating system file. Instead of just hunting for repeating patterns like a zip file does, this engine throws incredibly complex deterministic noise at the data to see exactly what matches.
So for every single byte of data, the system probes 2,048 noise candidates. It finds the mathematical residue of what doesn't match, and then folds it back in on itself, over and over again. It guarantees the accuracy using position-aware CRC checks. And here is the brilliant part. It generates self-healing parity bits during this evaporation process. So it doesn't just compress the data, it mathematically heals it. If a cosmic ray comes down and literally flips a physical bit on your drive, the math just corrects itself. It is actively fighting physical entropy. And the result of all that? A jaw-dropping 1,000 to 1 plus compression ratio on structured OS data. That means a massive 10 terabyte volume is squashed down into a mere 3 gigabyte physical residue journal. You're storing an entire data center's worth of information in a file smaller than a standard HD movie. It's wild.
Moving on to Section 3, the Neumann bypass, execution at memory speed.
So you've solved the storage problem. But how do you actually run software when every single byte requires searching through 248 noise candidates without completely melting your processor? They call their solution the HO10G1RM substrate. To hit native speeds on just regular commodity hardware, they built a divergence cache. By caching these divergent paths and using hardware prefetching, the system completely dodges cache thrashing. You know, that annoying bottleneck where a processor gets bogged down constantly searching for data.
If it's reading sequential data, it literally skips 7 out of 8 computational steps.
And this creates what the source code calls the Neumann bypass. This means the hypervisor fetches pre-computed results directly from the manifold rather than calculating them the old-fashioned way through the CPU's arithmetic logic unit. So, say you need to do a really complex encryption round, like AES. It doesn't actually compute the math. It just looks up the spatial coordinate where that math has already been resolved in the physical mesh. You are literally operating at the sheer speed of your memory bus.
To actually put this to use, the manifesto outlines these things called sovereign hooks. It allows users to bind high-level concepts directly to physical hardware coordinates using spatial scripting. You can literally take a phrase like "Hello World" and register it to the physical hex address 0x00ADDFE33. Any data piped through the system using that hook is deterministically forced through the topological mesh straight to that physical block on your hardware. It gives you this godlike physical control over the machine.
All right, Section 4, the Obsidian Workspace, a literal hardware projection. Let's move up the stack to the user interface.
The author stresses that this is absolutely not a simulation or just some standard graphical shell. What you're dealing with isn't an operating system just drawing windows on a screen. The workspace gives this elite-tier responsiveness because you are directly viewing the physical block residency of the hardware. It's a high-resolution pixel buffer projection perfectly synced up to a 100 Hz hardware interrupt. You are quite literally staring at the raw topological state of your machine, rendered simultaneously across 4 different phase offsets.
And the sheer scale of this is just immense. We're talking 1.2 times 10 to the 24th power. That is a staggering number of combinations within the 8-hop resolve rings, all rendered directly in the global state viewport.
To put that colossal number into perspective, the author proudly points out that the state space of this workspace visually and mathematically dwarfs the historic Enigma machine. I mean, Enigma had billions of combinations, sure. But this beyond Enigma complexity means breaking into this hypervisor probabilistically is virtually impossible. The state space is so vast, it's practically a universe unto itself. Honestly, good luck to anyone trying to brute force a password on this thing.
Finally, Section 5, the Bumgarner Puzzle, Future Roadmap.
This is the speculative architectural leap proposed at the very end of the manifesto. If the Phoenix release is the present, this is their roadmap for the absolute limits of silicon sovereignty. Right now, the system uses a highly complex master seed to define its topology, but the Bumgarner puzzle envisions an active state engine. Instead of relying on a static master seed, the machine will actively rewrite its own structure. It's exactly like a train laying down its own tracks just a millisecond before the wheels touch the ground. The manifold will embed its own mutations right inside the data stream it's folding.
Here's how that actually plays out. As data moves through the hardware, it leaves a really faint steganographic shadow on every single hop. The decoder then overlaps these shadows and reads them. The ultimate goal here is to create a puzzle where the hardware environment literally unfolds and defines itself based solely on the data passing through it. There's no central map anymore. The map literally writes itself into existence just in time for the data to travel across it. So, as we wrap up this explainer, I want to leave you with this really profound thought on the future of absolute silicon sovereignty. Can a topology truly derive itself from the steganographic shadows of its own data? Can a machine truly be designed to generate its own physical reality from the ghosts of its own information? If the Phoenix release is any indication of where emerging.systems is heading, the lines between hardware, software, and pure mathematics are about to get beautifully, incredibly blurred. Thanks so much for exploring this with me today, and keep your eyes peeled on the architecture of tomorrow.